Go live, and there we go. So we are live, yeah. So hello everyone and welcome to this seventh TinyML Aspirants Meetup. And this time we are joined by the great Michael from ARM. And like he's gonna give us a brief about what is Microtensor, popularly known as Utensor, and like how you can develop your tiny machine learning applications with them. And over to you.
All right. Thank you. My name is Michael Bartling. I'm currently a senior research engineer at ARM, but full disclaimer, Microtensor is not an official ARM project, so all of the content in these slides are my own opinions and not a description, or not ARM's. I have been working in the TinyML space for about 5 years now. I've worked both in the model transform side of things, like how you take your models and get them to fit on small devices. I've done a little bit of network architecture search research, and I've also been the principal architect on the Microtensor project in both our core and a good chunk of our code generation tools. So what is Microtensor? Microtensor is really just trying to make life easier when you're researching how you want your TinyML solution to look like. It makes things manageable. Roughly, who am I? I have, like I just described, I've been working on Microtensor for about 5 years now. I am a new father. I work at ARM as a principal research engineer, or sorry, as a senior research engineer, mostly working on some machine learning research and some security research. But moving forward, let's do some of the businessy bits. This graph is only a few operations. This is effectively just 4 ops, but once you run them through a lot of the model transformations that you would normally expect to see on a tiny device, you get a lot of extra nodes in your graph than you would normally expect. And going through and mentally managing these models can get challenging really quickly. So what Microtensor tries to do is simplify this approach. We want to make things as easy as possible for the runtime developers and as easy as possible for the model transform developers in the ML space, in such a way that they can work together. They can decouple some of their roles but still work together without having to worry as much about, oh, if I make this one little tweak, will it break something in my runtime? Or if I make some tiny tweak in my runtime, will it break an assumption about the model? So hand coding inference graphs is slow, tedious, error prone, and it's really write-only operation. Once you write it, it's going to become a black box and no one ever wants to touch it again. And that makes the model lifecycle management painful, especially in the emerging IoT world, where you may want to deploy before you actually have all of the data that you need for training your models. You also have strict RAM and ROM requirements, which is the standard embedded system story. Get the code working, shrink it later, it'll be fine. And that breaks a lot, because that means that you're going to spend more time and money on the actual circuitry in your system and less on the real value generation side of things. And a lot of times you'll even see heterogeneous memory architectures in these guys. So one model doesn't fit everything. You may have to do a lot of extra tuning, and that makes things even more challenging. And of course, with the inference optimization sides of things, it's a super active area of research. New techniques appear frequently. Quantization 2 years ago was 8 bits. Now people are even looking at 1-bit, 2-bit quantization techniques for various operators, and still getting similar accuracies in your final model inference. And of course, there's many flavors of embedded platforms and ML frameworks, and if you consider IoT in this, it just compounds the entire problem. So the Microtensor Doctrine, let's make things easy to use, easy to iterate, easy to modify, easy to extend, and easy to get help. It can't get much clearer than that. We try to make things in our core runtime almost look very similar to how NumPy would do it, or SciPy or scikit-learn, but still have the same performance or very high performing runtime code without having to put in a bunch of hacks. And a lot of this is just from our experience in consulting and actually trying to build applications that can fit on the tiniest devices with, say, like 2 kilobytes of RAM, and our general approach overall. So the 10,000 meter view of TinyML is, we've got a bunch of neural network frameworks, or just ML frameworks in general. Everyone has their favorite. We try to mux those together and output using some inference graph transforming tool, and we want to now generate code that'll run in a specific runtime. In Microtensor, it happens to be a direct inference graph. So code in equals code out, and you can go and tweak that graph depending on your use case. The TensorFlow Lite Micro approach is building a virtual machine. So you output a direct binary that can then be loaded and run in the runtime. But there's not much really stopping us from taking our code solution and wrapping it up in a virtual machine. It's just effectively a dispatch engine. And then there's also the super bleeding edge high performance stuff, which would be like MLIR, TVM, which is a direct model binary dump. So instead of loading up your model in a virtual machine, you have effectively an executable that you can link against inside of your specific application. But the next big challenge, especially something that's been emerging over the past 3-ish, 4-ish years now, is the heterogeneity of our target architectures. A lot of times we oversimplify our reasoning to just single device, single processor, but in reality, there's a lot of accelerators and things that you can leverage locally, but without things like full virtual memory or memory management, it can be challenging to schedule specific tasks. So if you have a compute engine like an NPU, you want to make sure that you have a compute engine like an NPU and you're trying to do firmware update, you have to be careful about your coherency. Can I do my model update hot, like as it's actually running, or do I need to wait until I'm done processing before I inject this update step? So Microtensor breaks up into the 2 main components: our core runtime, which I'm going to talk mostly about today, and our code generation tools, which do that muxing, taking a graph in and dumping out to an arbitrary runtime. And both of these are meant to be as extensible as possible, predominantly as a research agent. So some of the key ideas in our core runtime is tensors describe how data is accessed and where from. So you may have something like a SD card tensor or a RAM tensor or ROM tensor, and the performance of the ops depend heavily on which tensor you decide to use. Operators themselves, therefore, are tensor agnostic. They don't really care how the data is being read. I mean, obviously that's a performance hit depending on your choice, but again, that's a design decision. So the operators only care about read data from the tensor, let the tensor handle it, and the Microtensor runtime handle it for you, and add or multiply or depth-wise convolution, do whatever you want there. And we have an extension on that, which is the high performance operators, a lot of times the ones that are calling kernels that may be written in C or on a hardware device, can fetch blocks of data at once. They're the only ones that actually have the ability to access raw pointers of things. Obviously, we'll want to strive for low total power and execution and low static and dynamic memory footprints. But the one caveat on that is we also want to guarantee system safety. If we capture all of the tensor metadata and RAM data into dedicated regions that are managed, then we have the ability to guarantee things like system safety, so that if you run your model and in conjunction with, say, some IoT platform on your device, an asynchronous event in is not going to break your code, because we own our own dedicated region of memory, which can be used for other things. But for the most part, given a Microtensor code with its known model inputs and model parameters, we can guarantee successful running without without memory failures. Of course, you still can run out of memory locally, depending on your application code, but the default models won't fail unless you do that by accident. And this also helps us facilitate the heterogeneous compute, because if we control our own memory and we control the distinction between the metadata involved with our larger models or our internal data structures and the actual data that they refer to, then we can move things around quicker and we can better schedule things. So ultimately, the default tensor interface behaves a lot like a high-level language without sacrificing performance, and we're platform agnostic, so that you can train and test your models locally on your machine, and you should be able to at least get a good understanding of how they'll behave when you deploy them on your actual device. So what does this look like? Our high-level architecture is effectively, we have breaks up into two parts. We've got our core and our as part of the runtime, which really just describes our default contract with the system. It's what describes the data access pattern of a tensor and its life cycle, how operators are structured, how models are structured, and given any extensions on these types, we can still make all the guarantees that we stated in the earlier slides. And we also add a couple of extra things for convenience, specifically in debugging and memory management space, so that when you actually do deploy, you can make simple extensions onto the Microtensor core runtime that make life way easier when you're trying to debug or find error states or all the weird corner cases that can happen in an IoT deployments. And we've actually found that a lot of these has helped us internally track down bugs that we never even we never expected would exist. Okay, so I mentioned before that tensors describe the data access, but what does that really look like? Our low-level contract is effectively just this tensor interface that you can extend and build memory access patterns out of. But for the most part, these just look like wrappers around specific data sources. So we have a RAM tensor, ROM tensor, extensions on that, like diagonal ones if you only care about the principal components in your system. We have, you can extend them to also be over bus access devices or on file systems. And another case that we found has been really useful is building dedicated tensors for your input sensor sources. So if you are in virtual sensors, so say you're doing motion tracking or activity tracking, you may have a tensor that effectively handles the feature extraction stage, where I want to precondition my accelerometer and gyroscope into a new dimensional space. And then you feed it into your model and you don't have to worry going forward. But one of the main things that we've gotten out of these tensors is we can dereference. We treat tensors effectively like a pointer, and we dereference them similar to how you dereference pointers. And a good chunk of our code reuse in this space allows us to save a lot on footprint. It turns out that one of the biggest factors in the final code size of any ML runtime on tiny devices is actually your tensor management structures and how they behave. So we managed to shrink by being very careful in how we describe this basic contract. We've managed to save orders of magnitude in code size. The second big trick to saving a lot of space in tensors and also being able to guarantee the memory safety is using handles to recognize where the tensors exist. So in Microtensor, we have two predominant allocators. We have the metadata allocator and a RAM data allocator. The metadata just generally holds the object metadata and the object code data for tensors and various objects that exist in the Microtensor namespace. And the RAM data allocator is effectively like malloc. It's just some arena that we may own that you can read and write from. So the simplest case would be using system malloc, but that's actually kind of a dangerous idea because that breaks the contract that or the assumption that we made before in system safety, because if someone else makes a big malloc in a thread that you don't own, we could break Microtensor. So by owning these two allocators directly a priori in static global memory or in some dedicated memory space, then we won't break that. So given handles effectively just as a non-copyable reference to location in a metadata allocator or a RAM data allocator, we can now move tensors around directly, knowing with confidence that they exist in a safe space and in a safe state. And that means that with heterogeneous architectures, all we have to do is trust the scheduler or the context engine to do the copy for you. So on a dereference, if you don't own the specific block of data, it will go out and copy it after inserting a little bubble, so you don't have to worry about that. Then the operators, which operate on these tensors, now we get the guarantee that they're tensor agnostic. They don't care if you're using a RAM tensor or ROM tensor or so on. The only thing that they care about is read and write conditions. So is this tensor read-only or write-only or blah? And this gives us the ability to throw a lot more compile time errors and make sure that you don't accidentally break your code by trying to write to ROM, which would break your device really quickly. The next thing we do on top of this is we build a lot of fused operators internally and provide some optimized ops. So like Simsys wrappers, Simsys being a high performance ARM compute library for both DSP and for neural nets, or potentially NPU operators, which can further specialize on top of this. But something that we do try to do very carefully is up above in the right, you see the namespacing of our operators. We try to make our operators behave like the class of the op themselves. So if you wanted to switch between a reference operator, which just describes in a slow sense how to do a matrix multiply, with a high performance one, all you would have to do is change namespacing on that operator. And that's basically where we get onto this slide. We don't have to sacrifice a lot of system performance and code performance for this readability. If we're careful in how we structure the operators, then we get the readability side on the large graphs, and we still get the high-performing operators that behave inside of their class. So simple thing that we do in Microtensor is all operators maintain a named mapping of inputs and outputs. And this is effectively just an enum on the inside with a table lookup to the outside tensors that may be binded to inside of an operator. And all it costs you is a uint 8. So nothing too crazy. Now the real fanciness is how we do the scheduling and the memory controlling. Because we know certain things at the model transform side, we can actually guide the runtime to a more optimal solution of when tensors get allocated, when they get deallocated, and when events actually, what's the optimal ordering and reordering of the graph processing side of things to still get the solution that we want. And this is kind of how a CPU is going to do out of order processing. You don't really need to care. Depending on your low-level microarchitecture, you don't necessarily need to do operations in the same order if you can guarantee that you'll still get the same outputs in the same time. So by using a lot of this info, we can save both in our amount of time it takes to actually do inference, and we can reduce memory pressure. And the last little thing that we tried to add into Microtensor to make things easier is notion of error handling. We don't want full RTTI, runtime type information inside of our code, because that just increases our code size unnecessarily. So we cheat. We use some language features in C++11 to effectively compile time hash event IDs. And if we have this compile time hash of the event ID, we can store that locally inside of a plain old data structure type. And then we get all the benefits of having dedicated types. Errors are specialized errors, but they behave like a normal error, and events the same case. So you get a very Pythonic and very standard high-level language ability throwing these events, but you don't have all the system costs that are normally involved with doing that directly. So the internal Microtensor runtime will handle this for you as efficiently as we can. And then that also lets us control the size of these errors. They can be any normal integer size, so uint16, uint8, or uint32, depending on what your goals are in life. Then that also gives us an extra side benefit that we didn't originally expect, which is you don't have to have magic protocols around your error states and error naming and schemes, which is a very common practice in the embedded space. I don't know how many times I've worked on projects where it says it throws error dead beef, and then you spend 4 hours trying to figure out what dead beef actually is because they hide things behind pound defines in their structuring. We have the ability to just say, okay, given I know how the hash function works, I just run it through a simple program inside the hash function, which can scan my code base, output all the errors, and then just do a mapping of error ID to error type and grouping. Or even better, if I'm developing on multiple machines, say I'm just working with my a group off in Taiwan, I can guarantee that when they write out of mem error, it generates the exact same out of mem error that I do on my machine, even if it's targeting different architectures. So lots of cool stuff that we can do at compile time. So I've talked a lot about the core runtime. What does that mean for our generation tools? I'm going to quickly go through these because they are very complex, but a lot of what they do is similar to a compiler in nature. So they should be somewhat familiar to at least a chunk of the audience. If not, feel free to ask questions inside of the chat, and we can get to that at the end of the session. So model transform, the general flow. Like I mentioned, very similar to a compiler. We take some file input, which could be, say, like a TensorFlow TF-Lite file or your graph directly. We'll parse it and raise it into the microtensor intermediate representation, which is just our form of describing whatever an arbitrary process graph could be. We build transformers on that graph, which could be, say, like quantization or different quantization schemes, or dropout schemes, or ways to get rid of certain operators that we would never expect, or even make sure the graph is legalized. We'll do a final legalization on there, which will just make sure that this can even run in general on Microtensor, and do a simple optimization scheme. This effectively is the reordering I was talking about. And then we do the final stage of graph lowering, and this just targets a specific backend. For now, that's Microtensor, but we do expect to try to have other backends like TF-Lite or TF-Lite Micro and so on in our lowering engine. So if you wanted to do a research project on, say, memory scheduling or firmware update, you could just, all you really have to worry about is creating this graph transformer pipeline bits. So the front-end selector, this is the tedious part. That's where you go and describe individual inputs from TensorFlow, parse them, and do the graph raising. We provide a lot of mix-in, so you don't have to worry about a lot of the specifics in the microtensor raising. You really just have to worry about describing the front end that you care about. So for the most part, we have an example, and that's TensorFlow. But overall, this is beat your head against the table and just read through the doc sources and get things set up. The microtensor graph itself is actually fairly straightforward in nature. It looks just like a normal graph in Python. And since you have a normal graph in Python, it's pretty easy to process and play around with. The transformer pipeline, this is the real meat of everything that we do. And if you look at a compiler, the graph rewrite stage is also one of the biggest chunks of a lot of compilers. So we build a graph rewrite engine for you that finds a lot of the isomorphic matching of operators inside of your specific model and lets us find the closest equivalent. So we can do things like swap out reference operators for Simsys NN if you have that enabled in your configuration, or we could potentially fuse operations or things in the like. We can also do things like graph shrinking, like quantization, pruning, inline dropout, gating, for example, if that's available in your training pipeline. And again, helps us target more optimized results. Then the final bit inside of our code gen is our backend code snippet composer. And this is very, very simple. It's effectively a bunch of Jinja 2 templates, which given a microtensor graph and guarantees that we know it's legal, it will just dump out code. So, and this code is meant to be as human readable as possible and be able to be easily tuned. Alternatively, we could swap out this code snippet composer with a virtual machine-like thing. So instead of outputting direct code, we can output binary files, which can then be loaded into Microtensor later. So in conclusion, there's a lot of open research problems in TinyML. And this is the sort of thing that we're trying to really facilitate with Microtensor. On the core execution side, what really describes memory optimal virtual machine? Can we do streaming compression for IoT deployments? What constitutes an edge benchmark? And this is a big challenge, I think, currently an open area of challenge in TinyML space. So how can you test a series of models against a baseline data set, especially when you consider how geographic state may influence the conditions of your IoT deployments. So like temperature sensors where I'm at in Austin, Texas are they're going to get obviously a lot different data than temperature sensor over in India. So should models themselves in that regard specialize on geography in our deployments, or should we send a one model fits all thing? And then, of course, this is actually an older slide, but I say sub-byte quantization, but that's actually pretty common practice now. On the other side, what happens if the tech that we've built interacts with our training pipelines? We can do quantization-aware training. We could potentially do offline execution planning, target-aware hyperparameter tuning, and network architecture search, sparsity and lossy compression directly inside of our data itself, gating, basically saying like, only use parts of our graph when we're not confident in our solution, or use the whole graph when we're not confident in our solution, or only use part of the graph if we're very confident. We've seen this a bunch. If I'm detecting a cat in an image and I see like whiskers, okay, cool, it's probably a cat. I don't need to use the whole graph. And then, of course, partial code generation, especially if you're you don't necessarily know what your final deployment solution is going to look like, but can we generate the building blocks in place at training time to best optimize for everything? Thank you, and I think now it's time for questions. How am I on time? Perfect. 2 minutes fast.
Yeah, going great. Yeah. So I will just check back the questions. No, I don't yet see any kind of questions coming in from the audience right now.
Okay.
Maybe
cool.
like we can move on, then there might be any kind of questions coming in.
Awesome. I've got a very simple demo showcasing running Microtensor on x86 with the expectation that this could extend to any device. I just happen to have accidentally sent my device off for a consulting role recently, so I have to do this demo on my computer. Okay, let me know when the code size is big enough for people to read.
It's going great. Yeah.
Okay. So this this is effective. Let me go ahead and get rid of my bits over here. Let me briefly showcase like what an output model might look like. In fact, actually, I showed roughly what an operator could look like, and models are actually very similar. So let me jump over here and hold up, CPP. Oop. My model.h. Okay, so this is something that Microtensor would, it's a generated model. This is something I didn't write myself. It's something that our code gen tools built from a very, very simple TensorFlow graph. It's effectively A times B plus C plus D. So 2 adds and a matrix multiply for 2 by 2 matrices. So Microtensor will output a models constants folder, or here we go, constants.h. This is just something that'll probably exist in your ROM somewhere, or it could exist on an SD card. This bit doesn't matter. For now, I put it in ROM to make things nice and clear. I went ahead and wrote in a reference of our output, so something we can compare against. The model has one input, which is named input, and one output named output. And it's got 3 internal ROM tensors, B, C, and D, which we have over here in our reference. Of course, it contains its internal operators and 2 memory allocators. So the first allocator is the metadata allocator. This contains, as I mentioned before, all of the tensor header information and its internal object code. And the code generation tools will actually figure out the minimum size that you need for these allocators for them to still work. So in our case, we need 512 bytes for the metadata for all of our tensors. And we have a RAM data allocator, which is only 64 bytes in size, that these are meant to exist in static global memory for our model to run correctly. The actual model code that gets generated, it just simply propagates out for you. The big set here is in the model instruction, we just request in Microtensor to get the default metadata allocator and RAM data allocator and then set them to our local model, so set our context. We go ahead and declare the various tensors that we need for our model to run correctly. In compute, I went ahead and added a new event, which is I've started my model evaluation. So let's go ahead and notify of that. Let's make sure that we are running in the correct context. So reset, if we have multiple models, let's reset it to this current one. And then we just go through our operation. So multiply, add again, free as necessary, and then set our output over here. So in final outputs, we just set the outputs of our model to be the tensor output of the final add. In main, I describe my own event handler, which really just prints out the various events that I care about inside of my the model. So in this case, I just have a model start and model end, but we have a default event handler inside of Microtensor, so you don't actually have to do this if you don't want to. I specifically, in this case, declare my model and event handler in the global namespace because it's static global memory, and we get a lot of extra guarantees inside of the final runtime. So we know we're not going to blow up the stack, for example, and we know we're not going to pollute the heap. So this is a common layout when you're doing at least embedded engineering. And then our main, all it does is create a couple of buffers for our input and output data, which are going to be in system RAM, and we assign tensors to them. So in this case, a buffer tensor of size 2 and 2, it's a uint8, and it refers to this buffer that I don't own in Microtensor. This is one that's owned in user space, which I declare right here. So I give it a simple input, which is something that I provide. I think it's just 1, 2, 3, and 4. The models and then constants.h. Yeah, it's just 1, 2, 3, and 4. And I evaluate. So my model, set my inputs to my input. It's going to be my A buffer. Set outputs is going to be my output, owned in user space, and then just eval. And we can go ahead and compare our results against the expectation here. Now, something I did do inside of this model very specifically is I injected a very simple bug, which I'm not going to describe here, that causes Microtensor to throw an extra error state on destruction. So when the program is done and it's destroying all the objects, it will double destroy a tensor by accident. And that double destruction will throw a seg fault. So the fastest way that we can debug that is with our events handling system. So let me go ahead and clear this. I'm going to provide a simple cmake command. So in Microtensor, we built our entire build system is built off of cmake. So you can link, you can build Microtensor for your local x86 machine, and then you can test on your device by building a direct ARM binary and linking against it, or just getting the Microtensor build system integrated into your specific thing. So we provide solutions for Mbed, we provide solutions for Arduino, and a few others. But in this case, I just configure and make standard C++. I ran our demo directly. It would freeze at the end because we know that we get into an error state that the event handler determines. But quick thing here is we see that we have a model putting in a user buffer. This is what our A and B look like. Then we'll do output is A times B plus C plus D. We see model eval start and end, and then our final thing here. But you can turn off these events at compile time, so you don't actually need them. But we found that they're better to have when you're debugging. So in this case, we know we get into an error state, so I can just do simple debugging on this guy, break main, run. If I just continue all the way to the end, I know that I get into an error state. I'm in the error handler. Obviously, I know that this event is the actual error, so I'm going to copy that for now. So if you backtrace, you can go through it's the standard backtrace procedure, but if you're doing remote debugging, this would look the exact same as it would for local debugging. So the only difference is I have to set a remote device, connect to it if it's deployed out in the field, and then I'll still get the same list of things. I know that this is the error that happened. I know that allocator was bound. It was freed. This was going through tensor destruction. And inside of my model, oh, it must be here where I'm double deleting inside of my model and causing this thing to fail. So in this case, if I want to try to figure out exactly what the error that's being thrown is, I can either select frame, so frame, select, and then I think 3 is the one here. So frame, select 2. It's throwing a meta header not bound error, and this can only mean certain things. So if I leave and I recopy this event detected over here, say I only get the number and it's too expensive for me to run the debug, I can try to fake debug it separately. So if I go back into my main process here, I've got a little Python script locally that can find all of the events in my program, and it will compute the equivalent. It'll basically remap it out. So find error 5046, it must be meta header not found error, the same that I saw before. And that helps me dial in inside of my code and figure out where things are actually broken. And normally we don't really keep a history of these events and errors, but by injecting the capability of keeping these histories over time, we get a story of the higher level events inside of our graph processing engine that lets us really dial down and say, oh, I don't even need to go and do the full debug trace. I know roughly where in the code where I expect it to be broken, and I can go and fix that there. And that's it for my demo.
Yep, it was like great demo, to be honest with you.
All right. So any questions on the chat? Unfortunately, I can't see the chat.
I don't see any kind of questions coming in from the audience. Like they're fulfilled with the things like you have shown, and I've also shared some resources like the uh, Utensor website. Then there's the GitHub repositories and all those links and stuff.
Yes,
And I guess they're exploring them.
This demo is actually on my personal GitHub, so if you guys wanted to run through it as well, it's just github.com/mbartling. And then I also have a personal website, minionhut.com, where I go more into depth in a couple of the specialties of Microtensor and how it differs from other implementations of a TinyML runtime. So over here, if I close out of this and I go to minionhut.com, I'll have a couple of, right now there's just a couple of blog posts, but I have a few more in the pipeline. One on the events and errors, which I just described, and another on why we have 2 allocators and a lot of the cool guarantees that gets us. I will go ahead and stop sharing my screen.
Sure. So no questions at all. Going fine. So I guess like we have time for anything more questions. If anyone wants to lay down any kind of problems or stuffs that they are thinking of, feel free to post them in the chat.
Mm-hmm.
And in the meantime, check back. Nope. Seems we are going fine. Awesome. So I guess the time has come for wrapping this up, and it was truly a great demo by a great presentation. To be honest with you, Michael, and I guess like everyone is fulfilled with the demo and all those things, and they will soon start up exploring with Utensor and Microtensor.
Okay, and
That was it for today.
Yeah, if anyone has any more detailed questions on Microtensor, or if you're hacking on it and you need some help with something specialized, feel free to join our Microtensor Slack channel. We're pretty active on there. Microtensor has been a little bit quiet for the past few months, and that's predominantly my fault because I had my first child, and that's taking up a lot more time than I was expecting. But we do have a lot of cool things in our pipeline right now, and a couple of things that are will be announced soon. So yeah, look forward to cool stuff.
Yep, that was it today. Bye-bye, folks.